So far, we have reviewed the morphology of galaxies, but now let's take a look whether that morphology actually correlates meaningfully with some other properties of galaxies or their formation history. First, let me critique the traditional approach to galaxy morphology. It is subjective. It is based on the appearance, visual appearance in particular wavelength. Traditionally, those would be blue light sensitive photographic plates. But now we have panchromatic view of the universe, and when you look at galaxies in different wavelength regimes, they look very different. And classification would presumably be very different depending on which wavelength regime was chosen. Now we happen to have chosen visible light, and in vicinity of visible light, if you look at bluer wavelengths, ultraviolet included, you'll be very sensitive to star formation. So galaxies will be clumpier, there'll be more strong features due to the regions of star formation. If you look towards redder wavelengths, which are not so sensitive to star formation but reflect the bulk of the old stellar population, galaxies would look much smoother than that. So there are three major problems with the traditional morphological classification of galaxies. First, it is subjective. It is based on just visual appearance, looking at things and deciding whether some galaxies have more open spiral arms or not. However, these days we can actually process digital images of galaxies and define in an objective, consistent fashion some of those structural parameters. The second problem is that it's superficial. It really is based on just visual appearance in particular wavelength regime and not on actual physical properties that we'd be interested in, such as galaxy mass, for example. A more modern approach is to use correlations and clustering of different Galaxian properties in parameter spaces, and thus objectively define galaxy families using those correlations. Finally, it is an incomplete classification. It was based on what was known more or less in Hubble's days, and it completely missed a major dichotomy between giant galaxies. By giant, I mean those that are usually seen in Hubble sequence, and dwarfs, which turn out to be largely a completely different set of beasts, and I'll show you that later. And they themselves may split in different categories. So that was completely missed by the original classification schemes. All right, so what does it mean? Properties of galaxies, including their appearance, are a product of their formative and evolutionary histories. And thus, if we can interpret morphological trends, then we can learn something about galaxy formation and galaxy evolution. A lot can be already concluded from a very basic fact. Among the Hubble sequence galaxies, at least, there seem to be two dominant components, the elliptical-like bulge component and disk component. And the relative prevalence of these two determines a lot of properties of galaxies. The bulge/elliptical stellar components are older, and they're kinematically supported by random motions of stars. Stars have to somehow balance the potential wells in which they sit, and in elliptical galaxies and bulges, those motions are largely random, like molecules in a gas, so we call them pressure supported. In these galaxies, most of the kinetic energy is in circular motion around the center, and very relatively little kinetic energy is actually in random motion, so there is some. And so that's a major distinguishing characteristic. Note also that we've been just talking about light, and we already know that the dominant mass component is the dark matter. We think, with some justification, that dark matter is probably also pressure supported, random motions rather than rotation. And also, disks are certainly distinct kinematical age-type components, but spiral arms, which were used for original classification, may be largely ornamental. They are interesting patterns, but they do not seem to really correlate very much with anything else. However, having said all that, there are still very important and significant trends along the Hubble sequence. As we go from the early types, ellipticals and S-zeros, towards later types of spirals, SA, SB, SCs, there are several trends. The average age of the population decreases. The disks are younger, and the later Hubble taps are even younger. The star formation rate decreases. There is almost none in ellipticals and bulges, and more as you go towards the later types. Because of that, the color also changes, because young stellar populations are dominated by luminous blue stars, old stellar populations dominated by old red giants, and so there'll be trend from redder colors towards the bluer colors. The gas content will change, at least the neutral hydrogen gas will change. There is almost none in ellipticals and bulges except if it came from disks, and there is more and more hydrogen relative to the stellar mass as you go towards the later types. Likewise, the other components of the cold interstellar medium, including dust, are also increasing in their importance towards the later types. And finally, an important dynamical characteristic which tells us a lot about formative processes is that in the early types, most of the kinetic energy is in random motions. In the later types, most of the kinetic energy is in ordered circular motions. So because of these trends, and what they really mean in direct interpretation, Hubble classification persisted to this day. It's still useful, even though it's superficial and incomplete and all that. It's still fairly useful because it does represent some important properties of galaxies. Not all, but some. However, it does not represent others. For example, galaxy masses. You can't think of any more fundamental quantity than total mass of a galaxy. That is not contained at all in Hubble classification. In fact, here are plots of the mean values of important characteristics of galaxies, like radius, mass, luminosity, and mass to light ratios, as functions of the Hubble type. As you can see, these plots are largely flat, meaning there isn't dependence of these quantities on galaxy's Hubble type, except for some, maybe a little bit towards the latest Hubble types. If the Hubble type were representative or indicative of, say, galaxy mass, there should have been great correlations here, and there aren't any. So this is really probably the most fundamental problem with morphology-based classification as opposed to, say, physical properties-based classification. All of these trends can be interpreted in a simple way. They are really a sequence of star formation histories of galaxies. Not just star formation today, where there is almost none in ellipticals and a lot in spirals, and further away you go even more, but integrated over the lifetimes. Put simply, early types, ellipticals, bulges, formed most of their stars early on, and then very little after, whereas disks tend to have much more extended star formation histories, and they could be even flat, uniform star formation through the Hubble time. For some of them, the late type disks, star formation may be even still increasing in time. Here is an interesting little fact. Typical spirals, say like Milky Way, form stars at typical rates of several solar masses per year. And if you add up all of the hydrogen available for star formation in them, then it's usually about a billion solar masses or so. In other words, if spirals were to continue like this, they'll burn through all of the available hydrogen in a billion years or less. So it would seem as if we're really living at a special time. More likely, there is a fresh supply of gas. The fresh supply of gas that comes in from the intergalactic medium and gets still accreted on galaxies. And here is schematically what I meant by the trend in star formation histories. If you plot, say, star formation rates as a function of time, in ellipticals and bulges, there is a lot of activity early on, dies off very quickly, and there is hardly any after that. Whereas for disk galaxies, there may be a little enhancement in the beginning, but by and large remains flat, or as I mentioned, it can even be increasing. So this simple picture can explain all of the trends that we have seen so far. Now let's recall the concept of stellar populations. As you probably remember from earlier astronomy study, those were introduced by Walter Baade, who noticed that there seem to be two kinds of stars. There are younger stars that tend to be in galaxy disks, and older stars that tend to be in bulges or galactic halos, and he called them population 1 and population 2. So they differed in their ages and where they're found, and sometimes in metallicity and also their kinematics. Baade's ideas can be extended. You can think of stellar populations as subsystems inside galaxies. They're characterized by their location, by their density distribution, by their kinematics, by the star formation history, by the resulting metallicity, and so on. And there's probably more than two. For example, in the Milky Way alone, we can count at least four. There would be the old but metal-rich bulge. There would be old but metal-poor halo, much more extended. There would be young stellar disk, where stars are now being formed. And there would be older and somewhat thicker disk composed of older stars. Again, note, dark matter is yet a whole another issue here. How can we understand the connection between star formation history and dynamics? Well, schematically it works like this. Stars are essentially mass points, and even in colliding galaxies, galaxy mergers, they are behaving like dissipationless systems. They just follow whatever potential there is, and they, in a sense, dynamically remember the dynamics of their birth. So if you start with a bunch of small galaxies merging together in a random fashion, then stars that used to belong to them will continue to move in random directions, and you'll end up with a stellar system that is supported by random motions, which is just like elliptical galaxies. Now consider collapse not of galaxies already made of some stars, but just hydrogen clouds. They dissipate energy, but they cannot dissipate angular momentum. Therefore, they settle in the configuration that gives them minimum energy for the given amount of angular momentum, which is a flat, thin, rotating disk. Now they make stars. And those stars then remember dynamics of their birth, and they continue moving in circular orbits. There is very little in terms of random motions. So in this way, we can connect the dynamics of stellar populations or subsystems inside galaxies with the histories of their star formation. What about their metallicities? Remember that enrichment of interstellar medium comes from stars themselves. You form stars, massive ones explode, disseminate heavier elements they cooked up in interstellar medium. New stars are formed from that, and so on. Now, if you have a really massive big galaxy, supernova ejecta will not be able to escape deep potential well, and they will mix in with the rest of the gas, which serves as a fuel for the next generation of stars, and the metallicity will gradually increase in time. On the other hand, if you have a very low mass host system, a little dwarf galaxy or protogalactic fragment, the potential well is not so deep, and the kinetic energy of supernova ejecta is sufficient to expel them out into the intergalactic space, so that little galaxy does not evolve chemically very much. It does a little bit, but its metallicity remains low and doesn't change very much in time. So that's the qualitative picture, but let's try to put this in a quantitative footing. We would like to know about actual distributions and correlations of meaningful physical properties of galaxies that we can measure in well-defined fashion. And those include, first, the density distribution. How are they distributed spatially? What is the density profile? Their kinematical profile. How's the kinematics changing as a function of radius? The relative importance of old and young or rotating in random components, and the chemical abundances and how they change. So by and large, structural properties or density distribution are obtained through photometry or surface photometry, which is spatially resolved photometry. Pretty much everything else, kinematics, metallicities, star formation rates, comes from spectroscopic measurements. And in order to interpret these measurements, we have to use various population synthesis models and dynamical models. Dynamical models can be assumed as toy models with some gravitational potential, see where that goes. Stellar population synthesis models, meaning what kind of mix of different stars would it require to obtain spectrum as observed. And of course, because stars evolve in time, their mixture will evolve and the spectrum will evolve in time, and so we need galaxy evolution models like that. We have all of those, and we'll talk about them a little later. So next we will turn to the structural properties of spiral galaxies.